So the last thing that we talked about was Newton's view of how gravity works. We played with some of Newton's equations. We talked about using Newton's version of Kepler's third law. We talked about the law of gravity. That gives us a foundation of how gravity works. In astronomy, and especially in cosmology, you have to have a clear understanding of the role of gravity. Recall that gravity is one of the four fundamental forces. Gravity, weak nuclear force, strong nuclear force, electromagnetism. Gravity is the weakest of the four, and yet, gravity is king in many ways. We have to go a step further. We have to understand what Einstein has to say about gravity. That means that we have to talk about general relativity. Before we can talk about general relativity, though, we have to talk about special relativity. And before we get to that, we have to talk about what was probably one of the most important and spectacular failures in experimental physics, the Michelson-Morley experiment. So we're doing a sort of backwards engineering thing here. We'll go to page 46 in the workbook, the Michelson-Morley experiment. Now, some folks pronounce it Michelson, some pronounce it Michelson. Take your pick. Two things I want you to know about Albert Michelson. The first thing, he was the first American to win the Nobel in physics. The second thing that I want you to know is where he went to school. And this comes under the heading of my sandbox and my rules. So you need to know where Albert Michelson went to school. No, it wasn't Harvard, it wasn't MIT, wasn't even Orono, wasn't even SMCC. Here's where he went to college. All right, so there it is. So now you know. The first American to win the Nobel was a sailor. And so, yeah, we're kind of proud of that. So, what's this Michelson-Morley experiment? Well, to understand that, we got to talk a little bit about waves. So we'll start with the idea of sound. Sound is what is referred to as a mechanical wave. And mechanical waves travel through a medium. And if we talk about the medium of air here on planet Earth, that nitrogen-oxygen mix that we walk through on the surface of the Earth, it turns out that the speed of sound through the air is roughly 740 miles per hour, or otherwise known as Mach 1. The important takeaway is that the medium determines the velocity of a wave, the speed of a wave. And you may have had some experience with this just this past summer. Let's say that you were swimming around in a lake somewhere, and you took a breath and you dove under the surface, and you're piddling around a foot or three underneath the surface of the water, and you hear a motorboat, and you think, oh, damn, right on top of me. And what's everybody do? Well, they poke their head up, which kind of doesn't make sense, but it's what we do. So you poke your head up and you see that motorboat is really pretty far away. Well, why did it sound so close? Well, it's because in water, sound travels roughly 4 times as fast as it does through the air. So there's another example of how the medium dictates the velocity of the wave. So that gets us back to Albert Michelson. He was a scientist, and his specialty was light, the study of light and how it behaves. He came up with some of the most accurate measurements of the speed of light to date. This is back in the late 1800s, by the way. Everything that scientists knew about waves at this time indicated that for a wave to go from point A to point B, there had to be a medium. This is why, you may have heard this. There is no sound in space because there is no medium in space. It's empty space. So sound waves can't travel from point A to point B in space. Now, I love Star Wars movies as much as the next guy, but those explosions that you hear in the movies, it just ain't so. It doesn't work that way. So there is no sound in space because it's space. So the question was, how the hell do light waves go from point A to point B in empty space? Now, even though we didn't have powered flight back then, we knew enough about physics to know that the higher you went in altitude, the more rarefied the atmosphere became until you got to the point of space. So that was the big question. The big question: how does light travel in the absence of a medium? It just seemed to defy everything that we knew about the physics of waves. And so what we had was kind of a working hypothesis called the luminiferous ether, or the ether. It served two purposes. The first purpose was it was the medium through which light waves were propagated. This medium, this luminiferous ether, supposedly permeated everything. And again, this is a working hypothesis, not a theory per se, but a working hypothesis. Its other purpose it served as a universal at-rest reference point. Well, what do we mean by that? Well, if I stand still, I am at rest relative to the camera that's filming me. Oh, but wait a minute. If we do a little back of the envelope arithmetic and figure that the Earth, roughly 8,000 miles in diameter, spins around on its axis once every 24 hours, that means that at the equator, the Earth is spinning around at roughly 1,000 miles per hour. Here we are at roughly 45 degrees north latitude. That comes up to a little bit over 700 miles per hour that we're spinning around right now. Well, in reference to what? Well, in reference to perhaps an astronaut watching the Earth spin. Oh, so he must be at rest. Well, no, because the Earth is going around the sun at roughly 67,000 miles per hour. Relative to who? Well, an astronaut watching the Earth go around the sun. Oh, so he must be at rest. Well, no, because the sun is going around on the outskirts of the Milky Way galaxy as it spins. Well, then where is this one point that in space, in the universe, that we can point to that is not moving, by which we can measure all other movement? Well, that was what this luminiferous ether was supposed to serve as. So Michelson took a sabbatical from his naval duties and went to work at what is now Case Western University, and along with another scientist by the name of Morley, came up with this experiment. They got funding for it. They came up with this thing called a an interferometer, it's an optical device that is still used to this day. But this interferometer that they had built for them was the finest that the technology and the engineering of the time could furnish. This thing was so fine-tuned, so delicately, exquisitely balanced, that they discovered that if a woman was walking outside the building with heels, that alone was enough to make the thing shake. So what they did is they mounted it on a 1-ton slab of sandstone, as you can see in the illustration in the book, and then floated that block of sandstone in a pool of mercury. Now that's some shock mounting. And what was supposed to happen, if you see the diagram in the book, here's the sun, here's the earth, and we'll say June, and the earth goes around the sun, and here we are in December. This device would have registered either an addition or subtraction from the speed of light. Let me show you what I mean by that. You can take notes if you wish, or you can just watch. Let's say that we have a car at one end of a parking lot and an observer over here at the other end of the parking lot. The guy hits the horn, and those sound waves go across the parking lot at roughly 740 miles per hour. Now let's say if the car starts to move. We'll say 35 miles per hour. And he hits the horn, and the sound waves go across the parking lot. You might think that those sound waves would have a little extra velocity added to them as they approach the observer, but they do not. Remember, it's the medium. It's the medium that determines the velocity of the wave. So those sound waves are still going to go across the parking lot at roughly 740 miles per hour. But let's say that in the first scenario, there is a wind moving toward the observer at 35 miles per hour. And the car hits the horn. Those waves are going to go through that medium at 740 miles per hour. And then that 35 mile per hour wind will add to that velocity. And so, yes, in this case, if there is a wind, which is a better way to express that idea, if there is a relative motion between the medium and the observer, then that velocity may be added or subtracted. And so with a 35 mile an hour wind heading toward the observer and the sound waves going through that medium at 740 miles per hour, now 35 plus 740, those sound waves will hit the observer at 775 miles per hour. Only then can those velocities be added, because now the medium itself has a motion relative to the observer. So back to the Michelson-Morley experiment. We know that the speed of light is 186,000 miles per second. We'll do it this way. Okay. And so now here's the sun, and here's the earth going around the sun at roughly 67,000 miles per hour, supposedly through this luminiferous ether. Now, one of two things is going to happen here. If this luminiferous ether is the universal at-rest reference point, then Albert Michelson and his interferometer on planet Earth now have a relative motion to that medium. There is motion relative to the observer. There's relative motion between the observer and that medium. Therefore, this speed is either going to be added or subtracted to the speed of light on their detector. That's the rough street fighting description of what this experiment was about. And this, if there was such a thing as this luminiferous ether, then this experiment would have detected it, hands down. But what did they get? Nothing. No matter what they did, they could not either add or subtract to the speed of light with this experiment. That's the big takeaway from here. Nothing they could do experimentally could alter the speed of light. It was fixed at this speed no matter what. No matter what. And this is where it gets kind of weird. Think about what's happening here. Think about we have a school bus. Going down the road, it will say 35 miles per hour. Relative to an observer on the sidewalk watching that bus go by. And there's a kid in the back of the bus, and he tosses a baseball to his buddy in the front of the bus at, say, 10 miles per hour. Well, relative to you, those two velocities would add up. Relative to you, the observer on the sidewalk, that ball would be moving at 10 plus 35, 45 miles per hour. Okay? It's just like if you toss something out the window of a car at 60 miles per hour. You toss it out straight away from you relative to the car, but relative to somebody on the sidewalk, that projectile is moving at the same speed as the car. If you lean out the window and toss forward, your throw will give some velocity to that projectile, but the car's velocity will add to that initial velocity, and so they add up. But with light, this doesn't work. You can't add velocity to the speed of light. It's stuck right where it is. How the hell does that work? Well, that's where we're going to get, that's why we have to get into something called relativity. That comes a little bit later. Okay, now at the bottom of the page, there you see these two gentlemen, George Fitzgerald and Hendrik Lorentz. George Fitzgerald was an Irish physicist, and this story is apocryphal, which is a fancy way of saying it may or may not be true. But there are stories that say that it was George Fitzgerald, upon hearing about the Michelson-Morley experiment, said, well, in the absence of the luminiferous ether, then we'd have to say that all motion would be relative. Oh, we'll call that relativity, because you see, it was an Irishman who coined the word relativity. Okay, the Irish are a race of poets. Yes, we are. And Hendrik Lorentz was a mathematician, and he came up with a mathematical factor that enables us to deal with this seemingly impossible, wacky circumstance where you can't add velocities, and so that's where we get to what's called the Lorentz factor. We're going to spend some time with that. All right, so that's just the basic outline. This is one of those rare cases in which an experiment came up with a negative result that in turn throws a whole idea out the window. Bottom line, if the luminiferous ether existed as was hypothesized, this experiment would have nailed it. But because this experiment did not detect any variance in the speed of light, that threw the whole idea of the luminiferous ether right out the window. One of those rare cases where, yeah, it shuts it down. And so the idea of a universal reference point, that goes away too. And so in science, what we do is we publish our findings, we publish our work. And other physicists took a crack at this. They tried to duplicate it, and they got the same results. Nothing. So this is really quite ground shaking. But again, it also creates some problems. We'll get to that in a minute. The next couple of pages, I'm going to just lay out some basic ideas. You're not going to necessarily know their meaning just yet. This is kind of like handing out tools. I'm going to hand out some tools here for the next few minutes, and then I'm going to show you how to use them. So let's go to page 47, the Lorentz factor. And by the way, on the website, there are a couple of 3 videos that you can dial up where you can get into a little bit more depth on the Michelson-Morley experiment. But I just wanted you to have that background. But I do encourage you to take some time and watch those videos. Okay, so now page 47, the Lorentz factor, where we have square root of 1 minus v squared over c squared, and this is also referred to as gamma. Greek letter gamma looks kind of like a funky Y. This goes to determining time and length in relativistic situations. And I've laid out the formulas for you, where you see T delta equals T over square root of 1 minus v squared over c squared. Length equals length delta times square root of 1 minus v squared over c squared. And oh, that's a misprint. So let's correct that. In your book, I must have got fat fingered that night. So let me give you the correct one for length. The time one is, T is correct. Length should go like this. Length delta equals length times 1 minus v squared over c squared. So go ahead and make that correction in your book. And also below that, that needs to be rewritten. Length delta equals length times gamma. And length delta goes like this. Okay, yeah, so make those corrections. All right, so what's this length and T delta and length delta and all that stuff? Well, here we go. So T delta T delta is dilated or expanded time of a moving object as observed by a stationary observer. T time as experienced by the moving object. C, speed of light. V, okay, V is for the velocity of the moving object expressed in terms of c. And for example, if we had something that was moving at half the speed of light, we would say it would be moving at 0.5 c. Okay. Length delta Length delta is the contracted length of a moving object as observed by the stationary observer. And finally, length is the original length of the moving object. Yeah, that changes. All right. Okay. Relativistic velocities. Relativistic velocities are indicated by this, less than c. And relativistic velocities are velocities greater than or equal to 0.1 c. And it's a rule of thumb. It's not an exact thing, but generally astronomers and physicists refer to any velocity 1/10 of the speed of light or better as a relativistic velocity. Non-relativistic velocities are indicated by less than c. I'm not making that up. And these are velocities that are less than 0.1 c. Okay, finally, at the bottom of the page, what's this gamma all about? Gamma is the factor that allows us to compute distortions in both space and time given a specific velocity. These effects are most evident at relativistic velocities, but they do occur at any and all velocities. So I'll go through that again. Gamma is the factor that allows us to compute distortions in both space and time given a specific velocity. These effects are most evident at relativistic velocities, but occur at any and all velocities. Now, this gets us to another piece that's very important for us to have a handle on in cosmology. If we're going to talk about cosmology, then we have to gain an understanding, some understanding on the nature of space itself. And you'll see as we go along that we can't have a discussion about space without having a discussion about time. And it turns out that space and time are two sides of the same coin. That's why we call it space-time. They are inextricably bonded to one another. All right, page 48. Einstein's two postulates of special relativity. This is from 1905. Number one. The laws of physics are constant in any and all inertial frames of reference. That's Einstein saying that the laws of physics are going to work everywhere, in a nutshell. Number two. The speed of light is constant regardless of frame of reference. This is where it gets weird. Let me give you one other example of how this is weird. Let's say that we have an astronaut stranded out in space. There he is, floating out in space. Oh, here's our astronaut. There, see? That's an astronaut. And we're going to send a spacecraft out to go get it. And this spacecraft is going to approach the astronaut at 1/2 the speed of light, or 0.5 c, which means relative to the astronaut, that spacecraft is moving at 1.5 times 10 to the 8th meters per second. Well, let's say they got a spotlight mounted on the spacecraft so they can see him. So they turn on the spotlight and out come the photons. They leave that spotlight at c, the speed of light, or 3.0 times 10 to the 8th meters per second. So now we have the spacecraft approaching the astronaut at 1.5 times 10 to the 8th meters per second. It's got its spotlight on, so those photons are moving away from the spacecraft at 3.0 times 10 to the 8th meters per second. So how fast are those photons going to be going when they get to the astronaut? This fast. How does that even work? How does that even work? Well, that gives us a problem. So we'll pause here, take a few minutes, and read some of these other great quotes by Albert Einstein. He had a lot to say about a lot of things, and he was wicked sharp. But we'll pause here, and then we'll get into an actual problem. The best way to get a handle on this is to go through a couple of scenarios and thought experiments. So that'll be our next lecture.